Today we're going to look at total internal reflection, an important technology associated with it, and a natural phenomena associated with it. To start, total internal reflection, a refraction event that causes a perfect reflection inside of a material. That's for your notes. Pause if you need to. So it's called reflection, but it's a refraction event. Here's how it works. By the way, the light rays are going from the bottom to the top. The incident ray in blue is in the water, and the refracted ray in red is in the air. Starting from the left, if an incident ray crosses the medium boundary without any angle, there's no refraction. Moving to the right, in the second example, when the incident ray is 15 degrees, the refracted ray will be 20 degrees. Continuing to the right, if the incident ray is 30 degrees, the refracted ray will be 42 degrees. Next to the right, if the incident ray is 45 degrees, the refracted ray will be 70 degrees. By the way, have you noticed that in each of these situations, there's also a green reflected ray? By the law of reflection, the reflected ray is equal to the incident ray. But notice that the reflected rays are getting darker, which means they're getting stronger. And the red reflected ray is getting lighter, which means it's getting weaker. Remember that incident rays reflect, refract, or absorb, or some combination of these things. So the question is, notice the 3 question marks over on the right, is there some incident ray angle which produces a refracted ray of 90 degrees, or right on the boundary between the two medium? The answer is yes, and it's called the critical angle. All of the incident rays will be reflected. So for your notes, the critical angle, an angle of incidence that will produce an angle of reflection of 90 degrees. Any angle greater than the critical angle will cause total internal reflection. These reflections are perfect. They're better than any mirror can produce. Here's an example. Notice the image of the swimmer on the bottom surface of the water. There's a technology associated with this effect. It's called fiber optics. Fiber optics are used to send digital information to distant locations. Anything, video, voice, music, data can be converted to digital, ones and zeros. The ones are represented by light on and the zeros by light off. They look like this. They're made of glass or plastic, and they represent about $6.5 billion in terms of industry. They can replace copper. Copper's expensive. Glass, which is what they're made out of, is cheap. And you can see the difference in calls. That big copper bundle can only carry 50 calls, where that one fiber optic can carry 1 million calls. One fiber optic cable on the right, being held by someone, can replace the copper wire you see on the left. So I want to show you how fiber optics work. I've got this piece of plastic, and it's got a little crook in it. So one end is here, and the other end is here. And I've got a laser pointer, so hopefully you can see that. And if I shine the laser pointer in this end, you can see it coming through that end because light went through here, around here, and out through there. That's how fiber optics work. One more time. Of course, fiber optics aren't this big. Fiber optics usually are more like this and real thin. And let's see if we can do that again. So I'm pointing one end at you, and I've got one end here, and I'm going to put and hopefully you can see that. But usually fiber optics are what's called clad with cladding, which is just a black cover. So let's try that. Here I've got that end pointing at you, one end picking up the laser pointer, and hopefully you're getting that. You might have fiber optics in your neighborhood. FiOS stands for Fiber Optic System, but implementation has been very, very slow. So if you do have it, you're one of the rare neighborhoods that has it. Besides communications, fiber optics are also used for endoscopes. Endoscopes are inserted into bodily openings. Notice the doctor has inserted an endoscope into this patient's nose. That's a nose in the bottom near center of the screen. The endoscope can send light along fiber optic cables to the intended spot the doctor is interested in examining, and the video can be sent back along other fiber optic cables. Note the picture on the video monitor on the top left. If there is no opening, the doctor can make a very small one for the endoscope to fit into. The doctors are, in this case, are examining the patient's knee. The advantage of this is that a small opening will heal a lot faster than if the doctor had to do exploratory surgery. Okay, let's discuss rainbows. Recall that when white light goes through a prism, it separates into its constituent colors. By the way, this is caused by the different wavelengths of light, that is, the different colors, refracting at slightly different angles. After it rains, small water droplets are suspended in the air. As the light from the sun enters the water droplet, it acts like a prism and breaks the light into its different colors. The color rays hit the back wall, and because of total internal reflection, bounce off, and then the colors move back to the front of the droplet and exit, refracting again as it exits. So refraction occurs, and there's also a total internal reflection occurring. So how do you see a rainbow? After the rain stops and the sun comes out, have the sun behind you. You're back to the sun. The blue edge of the rainbow will be at 40 degrees up, and the red edge will be at 42 degrees up. And you'll see a beautiful rainbow. And who doesn't like to see a rainbow?